Hello, Algebra 1 students, and welcome back to your third lesson in Topic 4, Solving Systems of Equations and Inequalities. As a friendly reminder, our first 5 or so lessons are all going to be about systems of equations, and that's all part of our Essential Goal 12, and then our last 2 lessons will be about solving inequalities and systems of inequalities. So let's get started with our opener for today, and then we'll explain the point of today's lesson. So, our opener is actually going to have you solve 2 separate looking equations. On A, they want you to go ahead and solve each of these, or solve this system of equations, which has 2 different equations in it. And since they're both in, a reminder, y equals mx plus b, you'll probably want to graph each of them. Then on part B, they want you to go through and solve this equation over here and find x. So, go ahead, pause this, get started. Should only take you about a minute or 2, and then unpause to see how you did. Alright, just that brief reminder of y equals mx plus b, 3x plus 1 starts at 1. And then we use our slope, and a reminder, our slope is up 3 over 1, so up 1, 2, 3 over 1 from that beginning point, or left 1, down 3, left 1, down 3. We can go ahead and connect those to see our first line. Then we need to go through and do the green equation, the second one over here. Our y-intercept is negative 3. Don't forget that negative down there. And our slope has that negative out front. That means we go down 1 over 1. Down 1. We want to go to the right because we want our line to go in a negative direction, a downward direction. So down 1 to the right 1. And we go this way. Now we can connect. And I think our solution to this, and as a reminder, the solution to a system of equations by graphing is the intersection point. It looks like they intersect at the point -1, -2. Great. Let's go ahead and solve. Well, when we're solving an equation like this, I don't see any distributive property. We can't combine like terms here or here. So we're really on to the SADMET part of solving, right? We're on to addition and subtraction first. With addition and subtraction, my very first step is I always like to go through and get all the x's on the same side of the equation. How do we get them on the same side of the equation? Well, we use addition and subtraction. You could either start by undoing this positive 3x, but I'm more of a fan of undoing the negatives first, so I'm going to add 1x to each side, to its like term on each side. We don't distribute addition. So this becomes 4x plus 1 equals -3. Now that everything's to one side, we're going to continue with SADMEP, and we're going to look at just this left side and say, well, what do we need to undo that's attached to x? The 4 is multiplying, the 1 is adding, so we're going to undo addition still, and it looks like this. We're ending up with 4x equals -4, and our final step is to undo that multiplication with division. That leaves us with x equals -1. All right. Now, what was the point of this opener? Well, you might have noticed, or you might not, and you're going to now, that parts A and B have a lot in common. In particular, you might look at the 2 separate setups for the problems, or the 2 problems individually. And then also, you might want to take a peek at the answers. And what I'd like you to do is describe over on part C, what do parts A and B have in common, both in the problems and in the answers? Well, hopefully you notice that the problems are very, very similar, right? This 3x plus 1 shows up over here, and this -x minus 3 shows up over here. So if the problems look so similar, shouldn't the answers look similar as well? Well, if you take a peek at the answer down below, right, we have this guy right here and this one over here. What looks similar there? And you might notice that the x's look pretty darn similar. Do you think that's a coincidence? Well, it is certainly not. Because as we learned last class in section 4.2, if you have a system of equations and one of the variables is isolated, notice y is isolated right here, then you are able to take what y equals and substitute it into the other y. And when you substitute 3x plus 1 into the other y, we get this equation to the right. So part B is part A, but using substitution. So if they're the same problem, then I think that means that their answers should be the same. Are they the same? Well, they're not quite the same. Notice that part B only has the x part, the input part, so it only found the x coordinate over here. However, they are really showing us two separate ways that we can solve a very similar equation. So part B's answer is the x coordinate for part A. And so that brings us to the point of today's lesson. We're actually not learning anything new today. We're really just combining 4.1, which is solving by graphing, and 4.2, which was solving a system by substitution. And we need to realize that if you have two equations with y equal to the rest of the problem, then sometimes students will say, oh, you can just set these equal to each other. And they are right, but we need to realize that what we're actually doing is we're really performing substitution. We are substituting one side with x into y so that we can, quote, set them equal, end quote. What's also important to realize, though, is that we can actually work backwards. So if you were just given this equation here and said, solve this equation, and you just had that moment of brain freeze, and you're like, oh no, I don't remember how to solve it. Well, notice that we could pretty easily turn this equation into a system of equations. We can take each side of the equal sign, set them equal to y, and now we have a system of equations that you could solve by graphing. So if you don't remember the algebra and you like to graph, this is a really powerful method to solve the original equation. You solve by graphing, you look at the x coordinate, and that gives you the answer to the original problem. Why is that so powerful? Well, eventually, when you move up in math, there are going to be some problems, even later on this year, that we don't know the algebra to solve. But if you remember this trick of creating a system of equations, then that will allow us to graph the equations, which you might know how to do, and then find the solution. So let's look at another example down into our lesson. Given the equation negative 3x plus 5 equals 2x, create a system of equations and then solve it by graphing. Okay, so this would be like if your teacher asked you to solve negative 3x plus 5 equal to 2x. And you're like, oh no, I don't remember how to solve this. But never fear, systems of equations are here. So I'm going to go ahead and just do this cool curly brace. And some of my students say, oh no, I can't draw that curly brace. Am I going to fail? No, you do not need to draw the curly brace, right? And what we're going to do, though, is we're going to take this left side of the equation and make an equation that we can graph. The way we do that is we do y equals, and then the left side of the equation, negative 3x plus 5. We also need the second equation, 2x, and we're going to do y equals 2x. Notice both of these are equations that we should be able to graph. If this 2x throws you off, don't forget that you can put a plus 0 at the end. So graphing with me, y-intercept of 5 for my green equation, down 3 to the right 1 to keep that moving downward in a downward direction, down 3 to the right 1, down 3 to the right 1. And this should give us a pretty nice line. Y equals 2x plus 0 starts at 0, then moves up 2 over 1. Up 2 over 1. We can already see the point where the two lines will intersect, but I always like being complete. Helps me make a straight line too. And there we go. So we find that this system of equations crosses at the point 1, 2. All right, well, if we go back to the original problem, the teacher says, no, I don't want you to solve by graphing. I want you to show me the algebra to solve. Well, the nice part about being able to do this by graphing is we already know what the answer to this problem is. We know that x is going to equal what? Well, these were both equations with inputs. We care about this side. Those are all x's. I bet my x is just going to equal the 1 from the point of intersection. But let's double check. To solve this problem, I don't see distributive property, I don't see like terms, so we're on to the SA part of SADMAP, addition and subtraction. We want to move our x's to the same side using addition or subtraction, so you have a few options. You could subtract 2x from both sides, or you could add 3x to both sides. I think adding 3x to both sides is actually the most efficient way to do it, so I'm going to go the other way around. I'm going to actually subtract 2x from both sides just because some of my students did this, and I wanted to make sure you would know how to work it in case you went this direction. Negative 3x minus 2 more x's is negative 5x plus 5. And we're not going to do what some of my students do, where they say, oh, 2x minus 2x is 0, so everything including the equal sign is gone. Well, that's not true. An equation always has two sides, so on the right side of the equals, we actually need to put that 0. We need something over there. Then we focus in on the side with x and say there are two numbers attached. 5 is adding, negative 5 is multiplying. We're still in that undoing addition and subtraction, so we're going to undo adding 5. Gives us negative 5x equals negative 5. And now we can undo the multiplication. And we should see that negative 5 divided by negative 5 is positive 1. All right, just a friendly reminder, if you do create a system of equations like I did over here in the blue and the green from a single linear equation, that's this guy, do you need to find both the x and the y of the intersection? And the answer is no. We only need the input, or in this case, that's called the x value. All right, so just a friendly reminder. One way to solve this system of equations below is by substitution. So we're just going to show the first step to solve with substitution. You don't actually need to finish solving. Go ahead and try it. Remember, for substitution, we know what y equals here. So that means we can take this second equation. I'm not going to change the negative 6x plus 29, but I want to make sure that this equation only has x's in it. And so, luckily, we know what y is, so we can replace this y with the x's up above, 4x minus 1. Now we've created an equation with only x's in it, and you should be able to go and solve. I would probably add 6x to both sides first, but you don't need to solve, we're just doing the setup. Remember, because this is a system of equations, you'll need to find the x and the y. After you find the x, you'll substitute it back in and find the y. All right, but what if you were given an equation like this? 4x minus 1 equals negative 6x plus 29. Actually, that's what we have over here. And your teacher said, I want you to solve this. Well, originally you might think you have to use algebra. And algebra is probably the faster way. But if you ever get stuck or you want to double check your work, how could you solve that using a system of equations? Well, you create a system first. You use the left side, y equals 4x minus 1. And you use the right side, y equals negative 6x plus 29. Then graph. We're going to graph and find the intersection. And that's it. That is the point of today. The idea that if you have a system, you can create a single equation. If you have a single equation, you can create a system. And we're actually going to use those facts to help us understand a little bit more about our three cases of solving a system of equations. So let's go ahead and turn the page. You might remember when we first solved systems by graphing, we said that there were three options for what could happen when you solve a system. You could get two lines that cross in a single point. You could get two lines that never cross, that's no solution. Or you could get two lines, and some of my students are fond of doing this, and I think it's pretty clever, that cross in an infinite number of spots, so there would be infinitely many solutions. But we didn't talk as much. We did a little bit in the very first unit, but we didn't talk as much about what that looks like with an equation. So let's go ahead and try A, B, and C here. A wants you to solve this equation. B wants you to rewrite this equation as a system. Right? We have one equation and another, and then graph it. And then C wants you to explain the results of A and B. So go ahead and try both of those, and then once you're done, unpause, and you can see what my conclusions are as well. All right, so we're back. If we wanted to solve this one algebraically, my first step would be to distribute, right? We know distributive property comes first. And along with distributive property, because distributive property is all about cleaning up each side of the equation separately, we need to combine like terms. So this left side, positive 2 and positive 3 combine to make positive 5. Now some of my students got to this step and said, ooh, I can stop here, I already know the answer. And that's great. Don't forget to write the answer, though. You can't just leave that. That doesn't tell us. Your answer either needs to say x equals a number, infinitely many solutions, or no solution. Some of my other students, though, went further and they're like, okay, I remember we have x's on both sides. We need to undo the x's to move them all to the same side. So I'm going to add 2x to each side. And I think that's great. These cancel on each side, and that leaves me with 5 equals 5. Huh. Well, don't forget that this doesn't actually mean x equals 5. It means something else. And to remember the something else, let's pause here. We'll come back to it. And let's look at this as a system of equations. The left side of my original equation was y equals negative 2 times x minus 1 plus 3. And the right side was y equals negative 2x plus 5. By graphing, show that our answer has infinitely many solutions. So I think that's probably spoilers for what's happening over here, but let's double check that. The equation in blue is in HK form. HK form always gives us a point, a starting point, 1 comma 3, over 1, up 3. And then we, of course, have our slope, down 2 over 1. As we connect those, we get one line. Then we have the one in green, negative 2x plus 5. We know that this guy, or we should know that this is our y-intercept. So we start at 5, and we again go down 2 over 1. Notice we started at a point on the blue line, and we're using the same slope. So as we go down 2 over 1, we're just on the same line. So we go through and connect, and we should see that we have 2 lines right on top of each other. So, what does this tell us? Well, the first thing it tells us is that when 2 lines are on top of each other, we should know that's infinitely many solutions. And because this over here on A is the same problem, it tells us that this answer means infinitely many solutions. So for our conclusion over here, they wanted to tell us algebraically, how do we know when an equation has infinitely many solutions? So let's reference A. A is the problem we solved using algebra. What's the giveaway that the answer is infinitely many solutions? There's 2 things you need to reference. Well, first, I think we need to reference the fact that if you try to solve for x, eventually the x's will completely cancel out. There will be no x's remaining. And, well, what happened with the answer? Notice that the left side was equal to the right. So, and the left number equals the right number. I did mention that some of my students stopped early here, and that's because they realized up here that negative 2x plus 5 was exactly equal to negative 2x plus 5. So if you do realize that, you can stop early. The left side is exactly equal to the right. There are still x's, but that's all that really matters. But then what about graphically? What does a system look like with infinitely many solutions? Well, that's looking at part B. Infinitely many solutions occurs when the 2 lines are the same. And that's sometimes hard to tell. I bet most of us looked at these 2 and didn't realize right away they are the same line. It took us graphing to see that the 2 lines are on top of each other. All right, so we just talked infinitely many solutions and saw 2 ways to see that, algebraically and graphically. Let's go ahead and try one more before we conclude today with a couple practice problems. Solve the following system of equations by graphing. For B is based on our answer to A. What do you think the answer to this will be? Don't solve. And then for C, actually solve, and let's see if it matches part B. So let's start with 4A. Solve each of these by graphing. Well, the top one definitely looks like slope-intercept form. We need to start at 3, and then use my slope, up 1 over 2, or down 1 to the left 2. Line was a little down. I could do better than that. There we go. The second one can throw a few people off, this negative 2 plus 1/2 x. You might want to rearrange it first. You might want to put the mx first and the plus b at the end. That shows us we start at negative 2 and have the same slope, up 1 over 2, or down 1 to the left 2. What can we say about those two lines? Well, some of my students said, "Ooh, they're perpendicular." And that was actually very good because they remembered there are two special types of lines that we studied in the last couple of units. Those lines are parallel and perpendicular. Perpendicular lines, though, cross each other at perfect 90-degree angles. They cross. So these are not perpendicular. These don't cross. These lines are parallel. And as a reminder, because they don't cross, parallel lines have no solution. In fact, you'll notice here that we could have seen they were parallel early on because they had the same slope but different y-intercepts. Now, if you look at this guy up here, they also had the same slope, but they didn't end up being parallel. They ended up being the same line. So yeah, when your two equations have the same slope, or if you're looking at two sides of an equals and they have the same slope, your answer is either going to be infinitely many solutions, or, in this case, no solution. So if you were given this equation and said, "We want you to solve it," you could hypothesize, you could guess based on what happened on A, and noticing that they just took one equation and set it equal to the other, so this is really the system over there, that this answer is probably going to be no solution. How do we prove it? Well, we look at the last one. We actually use some algebra. We're going to bring the x's to the same side by subtracting them off. But when you do that, because they are the same value on each side, they cancel, and it leaves us with 3 equals negative 2. Is 3 the same number as negative 2? Well, no, it's not. So what does this tell us? Well, we should probably write a quick conclusion here just for your notes. When the x's cancel and the left number, what do we say about 3 and negative 2? Oh, is not equal to the right number. Oops. The answer is no solution. So we do need to be able to recognize that when we get two numbers not equal versus two numbers equal, they are two different types of answers. Infinitely many solutions when they're the same line, same answer, or no solution, different y-intercepts in this case. All right, our last part for today, if you have extra time, I did include a bonus page at the end. If you're, it's totally super far ahead and the rest of your class is dragging behind, there are some practice problems here, and they're good ones. You'll need a separate piece of paper. But everybody's exit ticket for today is this last problem. It says using any method, graphing or substitution. Most of my students found these hard to graph, so I'm really going to suggest you use substitution. Solve each system of equations. Out of the 4 problems below, A, B, C, and D, only one of them gives no solution, and only one other gives infinitely many solutions. The other 2 problems have solutions, and you need to list those in x, y form. So I'm just going to quickly write 2 blanks with x, y. We're not going to use those in all 4 problems because one of them has no solution and one has infinitely many solutions, but we'll at least set those up for us later on. As a reminder, as you go through to solve, you're really trying to make sure for your first step that there is a variable by itself. On A, you certainly have a variable by itself. But on B, C, and D, no variables are alone. So your first step on B, C, and D is you will need to isolate a variable, then substitute. So, good luck. You can work in order or out of order, whatever sounds good to you. If you get stuck, you can hit play. If you want to check your answers, you can hit play and fast forward. I'm excited to see your success. All right, let's get to this. So for our first one, we know what y is equal to, so we're going to work with the other equation. This gives us negative 16x plus 2, and then not y anymore. We want everything to have the same variable, and we know what y is equal to, so we'll leave a blank, equals negative 2. Since y is equal to 8x minus 1, I'm going to replace y with 8x minus 1. And then we can go ahead and distribute. Negative 16x plus 16x minus 2 equals negative 2. We should combine like terms. When you combine negative 16x and positive 16x, I think that makes 0x's. And several of my students in the past have struggled with that, and they've said, oh, 0x, does that mean I just put an x here and then I leave a minus 2 equals negative 2? And actually not, because anytime you have a variable by itself, what do we assume the number is that's there? We always assume that's a 1. So by putting x, you're telling me that negative 16 plus 16 is 1x. It is not. In fact, these two make 0x's. And although you can write 0x's, if there are none of something, we just don't write it at all. And so we are down to negative 2 equals negative 2. There are no variables left. This is a situation we covered on the previous page. When you get negative 2 equals negative 2, those are equal to each other. So this is a case of infinitely many solutions. Now, if you had graphed each of these, this is in slope-intercept form, that's not bad, but if you had graphed this one as well, what would have happened? Well, they would have ended up being the exact same line. All right, let's move on to B. Part B. Which variable looks easiest to isolate? I think this y. Okay, and I'm going to be a little lazy here. The 2x is a positive 2x. It's adding to y. So I'm going to undo the 2x by subtracting 2x from each side. 2x minus 2x is gone. 3 doesn't combine with the negative 2x. So I've really made a new system where the top equation is y equals 3 minus 2x, and the bottom equation hasn't changed at all. We can now see that y is isolated, so we can do our substitution. We take this second equation, 2x plus 9, and we will need to replace the y with what it's equal to from the first equation. Y equals 3 minus 2x. Same steps each time. We now distribute this 9 into the inside. That gives me 2x plus 27 minus 18x equals 27. Combining like terms, I see 2x's minus 18 more x's. You're at a very small positive. You're taking away 18. We got to be at a negative. 2 minus 18 will give you negative 16x's. Plus 27 equals 27. From here, we're trying to isolate x. I see two numbers attached to x. Negative 16 is multiplying. 27 is adding. Let's undo the addition first. Like so. This gives us negative 16x equals, 27 minus 27 is 0. Well, there's nothing on the right side, so we do need to write in the 0. Now, once we're here, some of my students said, oh, it equals 0. That's going to be like a no solution. But be careful. We can continue isolating x. We can divide off the negative 16. This is gone, and it leaves us with x equals. What is 0 divided by any number? And you can try on your calculator 0 divided by negative 16. You should get 0. And don't be mean to 0. 0 is a number. It's the number in between negative 1 and positive 1. Right? There's a 0 on an x-axis. What this 0 is telling us is that these two equations up here, the original ones, cross at a point of 0, comma something. Now we're not done because we need to go back through and find the y, right? This y is missing down here. So we need an equation that uses both x and y because we're going to have to turn the x into a y. Well, jumping back up here, I think I see an equation that I'd prefer to use. You could use this one or this one. I'm, however, going to use this guy. I always like an equation where a variable's already isolated. So I'm going to use y equals 3 minus 2x. So I'm going to use y equals 3 minus 2x. And I'm just going to substitute in my x value that we found, which was 0, and then work to the right. 2 times 0 is 0. 3 minus 0 is 3. And that tells us that our line crosses, or the system has a solution at the point 0, 3. All right, moving on to part C. Part C, there are 4 different variables. None is isolated. I think in this case, the x is actually going to be really easy to isolate because currently x is being subtracted by y, but we know how to undo that. We can just add y to each side. These will cancel. And so we have a new system. I'm actually going to show this one twice, where x is equal to 0 plus y. My second equation, 5x minus 2y equals 6. Now, most of my students actually preferred to keep the 0 in here. However, don't forget, whenever you have a 0 adding or subtracting, you can really drop that 0. 0 plus anything is just that thing. And so I think as you get more advanced in mathematics, students will prefer this because it's less writing. However, since my students said they found this one easier, I'm going to work with that. Totally try the second one if you prefer that one. So here we go. We know that x is equal to 0 plus y. So we're going to take the second equation. 5, we're replacing x this time, and we're replacing x with 0 plus y. To solve, we need to distribute. That will give us, let's see, anything times 0 is 0. 5 times y is 5y minus 2y equals 6. Well, we actually don't even need the 0 there. And when we combine like terms, 5y minus 2y I think gives you 3y's. And now, since we don't even need to write the 0 in front, I think we can finish solving. You could ask yourself 3 times what equals 6, or just divide off the 3. Y equals 2. Great. Now we need to put the 2 down there and move back to the originals and think which problem or which equation has both x and y. And there are many of them. You could use any of the originals. I've told you before I really like when an equation is already isolated, so you could use this guy, or I'll be really bold and even use this one over here, x equals y. So if I want to use the equation x equals y, and we know that y is 2, then now it's solve for x. Oh wait, x is already isolated. X is 2. Right? This equation up here, x equals y, tells you whatever the x is, the y has to be the exact same thing. Since y was 2, x must also be 2. Last problem. All right, this one's a little bit trickier because I think a lot of you would say, ooh, we should isolate this y here. And I am going to isolate the y that's right here. But it's trickier because not only is there a 3x adding to it, there's also a negative 1 multiplying. And so just using a few years of experience that I have, I'm going to go through and isolate y in a different way. The very first thing I'm going to do is I'm actually going to add y to each side. And the reason I'm doing that is I really like y to be positive. It saves us from having to divide by a negative and make a silly mistake. So this gives me 3x equals negative 2 plus y. Since eventually I want to isolate y, let's do one more thing. What's still attached to y? Well, the negative 2. So I'm going to add 2 to each side. And that gives us 3x plus 2 equals y. So what did I just do? Well, we have a system of equations where I didn't even touch the top equation, but the bottom equation I did change, and it became 3x plus 2 equals y. All right, here's y. We know what y is equal to, so that means I'm going to replace the y in the top equation, and so we'll jump down here. Negative 18x plus 6 will replace the y, equals 24, and the y is 3x plus 2. Let's continue solving. The 6 distributes, lots of arrows there, sorry. Negative 18x plus 18x plus 12 equals 24. And combine your like terms. Negative 18x plus 18x, whenever you do a negative and a positive of the same, we say they're additive inverses, they cancel each other out. And that just leaves us with 12 equals 24. You should note that 12 is not equal to 24. So what does that mean about our solution? There's no x's left and we got unequal sides. Well, what that means then is there is no solution. If you were to graph these two original lines, they are actually parallel lines. And notice that's pretty hard to see here. Parallel lines have the same slope. And you might say, well, this is negative 18, then this is 3. Those are the numbers in front of x. Those aren't the same. But you need to remember that you can only see the slope when y is completely isolated. So we isolated y down here. This is a slope of 3. But we certainly didn't isolate y over here. And you'll find when you isolate it, this also turns into 3. They are parallel lines. Parallel lines have no solution. So hopefully you got some good practice today. Just to reiterate what we discovered, we really exposed the connection between solving a system by graphing and solving by substitution. We said that if you wanted to solve a system by graphing, you could, or you could turn it into an equation using substitution. And the other way works as well. We could reverse the process, where if you have an equation and you didn't want to solve, you could create a system of equations. That allowed us to see the connection between infinitely many solutions algebraically and with graphing, and no solutions algebraically and graphing. Thank you for tuning in. Next class, 4.4, we're going to be introduced to our last method to solve equations. Excited to have you back then.